Now, we said we'd talk about periodic table this section, and predictably, we have a periodic table. Now, of course, it need not be this large. It can be smaller, or even the size of a, what you want to call it? One of those little cards. Postcards? No. Name cards? Yeah, closer. So, what's this line here? This line separates the metals and the non-metals. Technically, hydrogen is considered a non-metal, but it does exhibit certain metallic properties at times, such as a tendency to be H plus instead of H minus. Now, okay, hydrogen is unique, it says so here. Many physical properties of non-metals. Why? Well, it's a gas, it's not lustrous, it's not a shiny liquid or solid, although only one metal is a liquid at room temperature, and that is mercury. One non-metal as well, that's bromine. These two are the only liquids at room temperature and pressure. Now, hydrogen has chemical properties of metals, specifically the chemical properties of alkaline metals, in that it loses an electron for most of its ionizations. Now, an alkaline metal is basically guaranteed to lose one electron when it ionizes. Now, these are soft metals. So what do you think is happening here? Well, it says that they react violently with water. So here we have, well, one of them. Here we have another one, and here we have a third one. Which one do you think is which? Well, so lithium, sodium, potassium, and so on. Rubidium and cesium tend to be kind of expensive, so for the most part they would not be able to find images of somebody being dumb enough to actually chuck cesium into water for a textbook's purposes, or our image purposes even. So, what's this? Well, this is lithium in water, so it's bubbling fiercely, but it's not quite exothermic enough to explode, to combust. Why? Because the reaction is not proceeding fast enough. Why is that the case? Lithium has a relatively high melting point compared to sodium and potassium. So, as one of the trainers at Canadian Chemistry Olympiad in 2011 said to me when we were doing training at the University of Montreal, okay, you drop lithium into water, okay, I mean, it's going to fizz and stuff, but generally no problem. If somebody drops cesium, run. But the thing is, you usually can't have so little cesium to work with that, well, other than the fact that it'll explode in your face, it usually won't be quite as spectacular as this for a very long time. It'll just boom, and then it's done. Now, alkali metals have to be kept under oil, usually kerosene, to prevent reaction with air. Or it can be stored in a vacuum. Air? Why does it react with air? Well, air contains both oxygen and water vapor. So if it does this with water vapor, and we know that it's easy for it to lose electrons, incredibly easy for it, in fact, and oxygen likes to gain electrons. It's got a very high electron affinity. Well, what happens? If it touches oxygen, it will oxidize very, very quickly. This is why when you take it out of the oil and you cut it with a knife, you will see the surface literally darken before your eyes. And what's that? That's an oxide coating. Well, slightly less reactive and less spectacular are the alkali earth metals. So they're solid at room temperature, just like the alkali metals, and all metals except mercury for that matter. So they show metallic properties. What does metallic properties mean? Metal. Ductile. So you can stretch it, and it will be stretched into a wire without breaking very easily. Although it'll break eventually. But you can stretch it into a wire. Whereas, imagine trying to take a piece of chalk and stretching it. Yeah, that just snaps. That's brittle. So the opposite of being ductile is to be brittle. Now this is usually lustrous, which can be summarized by the word shiny. And what else? What else do you know about metals? Well, they are conductive of both heat and electricity. And electricity. And they are almost all solid. They also tend, well, okay, hardness varies. What other traits can you think of? Well, we'll be talking about these traits later on. But these react with oxygen to form this type of oxide, MO, solid. The little S indicates it's solid. What happens if it says L? That's liquid, right? And what about G? Gas. And sometimes you see AQ. This means aqueous, i.e. in water. In water solution. Now, all except beryllium will react with hydrogen to form hydrides. Now, reacting with hydrogen is generally considered fairly difficult because forming H- is far less stable than forming H+. So they react with water to release hydrogen. What does this say? Well, to make MOS, or in this case M, hydrogen, and so say magnesium hydroxide. Well, here you have 2 H2O becoming 2 OH-. What happens then? You have 2H+, right? But the metal is going from just M to M2+, which means it's losing 2 electrons. 2H+ plus 2 electrons means H2, gas. Now, transition metals, while they're less stereotyped than the alkali and alkaline earth metals, they are also, as a result, less predictable. So a wide range of chemical and physical properties. I mean, we know that, say, zinc reacts fiercely with acid, whereas iron reacts much slower. And, well, these are generally strong and hard, although I do not recommend you test the hardness of mercury, given that it's a liquid at room temperature and also very toxic. And most of them have high melting points. Well, there's few exceptions. Mercury, of course, as previously mentioned. And even outside these transition metals, there are still metals that have interesting melting points. For example, let's look at our little one. So gallium, which is next to zinc, will melt in your hand. But it's not very toxic. Now, what else? Oh yes. Tantalum, which is down here next to tungsten, melts at a very high temperature indeed. Tungsten has a melting point of around 5,000, if I recall correctly, Celsius. Now, you are not expected to actually memorize hard numbers for any of these. Why? Well, at least in the North American education system, you would not be expected to do so. Only know that mercury and bromine are liquids at room temperature. So, within the transition metals, we have the lanthanides, which are elements with atomic number 57 to 70, and the actinides. Now, these begin to include artificial elements, which are not found in nature. And they are listed beneath the main table. Why are they listed here? Well, when we start talking more about different electron orbitals, This side is the s orbital. This side, these 6 columns, are the p orbitals. These 10 columns are for the d orbitals, and these 14 columns are for the f orbitals. But those suborbital splitting patterns will be discussed far later. Now, the actual arrangement was because of properties, like reactivity and such. So, past uranium, we call these transuranic, because uranium is the heaviest element that occurs in nature. Anything with number 93 or greater, atomic number that is artificial. Now, some of them are stable for relatively large amounts of time, such as plutonium, whereas some, such as ununceptium, have barely managed to even be synthesized successfully. Now, some of them don't even have names, as you may have noticed when I said ununceptium. It literally means 117. So, noble gases. Alright, remember when we talked about these previously? So they're the gases at room temperature. Why? Because they're already in a stable octet. They don't have very much in terms of intermolecular forces, and they're one atom in terms of the particles in the gas. Some gas particles are 2 or more atoms, such as water vapor or oxygen, but these have particles that are just 1 atom, so they're monoatomic. So they're gases at room temperature. They have low melting and boiling points. Why? Because with a single atom, it's hard to have affinity for any other atoms if you're already stable. Now they're extremely unreactive, so krypton, xenon, and radon, i.e. after the helium, neon, and argon 3, these will reluctantly form compounds with fluorine. Radon is radioactive, and it is recommended that you not live in the basement due to radon, because one of the more common sources of radon in homes is from groundwater or other natural incursions of gas through cracks in the basement. Of course, there are radon detectors available, but there is a correlation of how much radon versus how much cancer of, say, the lungs you get. So try to avoid it. So what are halogens? You may have heard of halogen lamps. Now, halogens, they might be solid, liquid, or gas. Why do we say they might be solid, liquid, or gas? Well, fluorine at room temperature is a gas. Chlorine is a gas. It was the first gas to be used as a poison gas in chemical warfare. And what next? Oh, bromine. Hey, didn't we just mention bromine? It's the other liquid at room temperature. And then after that we have iodine. And after iodine we have, they don't list it. Why? Because really astatine starts to show some more metallic properties. Now, most of these diagrams, when they do the periodic table, they show the metalloids. The metalloids, many depictions of the metalloids include astatine. Some, for some reason, don't. So just the real halogens are basically these first 4. Now, these are not lustrous, just like most nonmetals. I mean, I do not think that the oxygen particles floating around are shiny, are they? No, they're not. So they're also not conductors of electricity unless they're reacting and forming ionic compounds. And these ionic compounds are either melted or in solution. So they're extremely reactive, especially fluorine. Hydrofluoric acid, which is a compound from fluorine and hydrogen, is able to etch glass. Now, All halogens will react readily with hydrogen to form acids, metals to form stuff like FeCl3, and even other nonmetals, which is why chlorine gas was used as the first poison gas back in the First World War. Now, we call these first two groups of metals and all the nonmetals, and as well as the metals from group 13 to 18. Where are these? Well, these are the tall groups, right? Besides the transition metals in the middle. We call these the representative elements. Why? Because they are somewhat more consistent in terms of properties per group than the transition metals. Of course, that doesn't stop copper, silver, and gold from all being very excellent conductors. So at least they're united in that. But most people are hard-pressed to find too much similarity between zinc, cadmium, and mercury. Now, we just said group. It says groups 1, 2, and 13 and 18. 13 to 18. Well, what's a group? It's a column. Sometimes it's called a family because of their relative similarity to each other, whether in terms of reactivity or other traits. Now, a period, well, it's called a periodic table for a reason. Every once in a while, the traits start repeating. So, that's a periodic pattern, right? So, a period must be a whole row. The periodic law is a rule developed from many observations stating that when you arrange these elements in order of increasing atomic number, their properties will repeat eventually in a certain pattern. Now, there are several alternate depictions other than Mendeleev's periodic table, which we already looked at. This one. This is by a guy named Dmitri Mendeleev. Well, the initial version was. There have been alternate versions, such as listing them as like the spiral arms of a galaxy, and various other even more insane-sounding schemes. However, the periodic table appears to be here to stay.
等一下，唐哥，你回去把那一个颜色一个颜色的这样的上面那黑板上颜色标的有这一行是什么，这一行是什么，你说出来多好啊！你没有对照表说谈这的时候。So let's review the table. 看一下你要你的。
行。So let's review the periodic table. Well, alkali metals, first group, except hydrogen. Alkaline earth metals, second group. Transition metals, groups 3 to 12. Lanthanides and actinides are these. They begin with lanthanide, lanthanum, and actinium. So, halogens are 17, but most people don't bother including astatine in there. And noble gases are group 18. Now, what is this? This little ladder here divides the metals and the nonmetals. Most of these elements that stride across this ladder are counted as metalloids. Now, most people only count boron, silicon, germanium, arsenic, Sb, tin. No, tin is that one. Sb is antimony, tellurium, and astatine as the metalloids. Polonium is not counted as a metalloid because it behaves too much like a metal. Now, it may kind of surprise you that selenium, which is known to be hazardous in large amounts to human health, is labeled a type of metal poisoning, not considered a metalloid, nor is it considered a metal. Now, continuing, we consider another situation that only really matters for the representative elements, Lewis symbols. Now, carbon, which has 4 valence electrons, would be represented as this. Hydrogen, which has 1, would be represented as this. Here, we show the hydrogen bonded to the carbon, by using either a pair or alternatively we could use a line. Now, what is this molecule that I'm drawing? This is methane. Now, I have shown both conventions of drawing Lewis diagram bonds. Now, if you've heard of the term Lewis acids and Lewis bases in relation to acidity and basicity, we will be learning that eventually, but that's for quite a distant future. So, it consists of the chemical symbol, as you can probably tell, CH, yeah. And dots to represent the valence electrons. This is a form of electron dot diagram that's often used for reaction process diagrams. Wait a second, what's a reaction process diagram, we might say? Well, say we're forming a bond. So we have OH minus. This is a hydroxide, which is basically means that this is a base in solution. And we have a proton. So here we form a bond, and now we have, ta-da, water. So this is what we mean by reaction process diagrams, although for the most part, these would be more prone to saying, oh, a hydroxide radical and a hydrogen radical each donate one electron to make a bond, and then, yeah. So, this is going to be in the future. For now, in summary, the periodic table is an arrangement of the elements that exhibits a pattern. So, each group has relatively similar reactivities and other traits. Now, there are other patterns in the periodic table that we will be discussing in the next section, such as electron affinity, ionization energy, atomic size, and so on. So, all elements in the same group have the same number of valence electrons. Didn't we just mention that valence electrons are the main things that are involved in chemical reactions? Well then, they have similar chemical properties, so similar reactivity and such. Okay, that makes sense, right? Now, they can be represented by Bohr-Rutherford diagrams or by Lewis symbols. Both show the number of valence electrons. Bohr-Rutherford also shows the number of other electrons and other orbitals, but Lewis decided to easy mode it. I mean, given how you know that all people are lazy, or how you should know this by this point, it should be no surprise that Lewis symbols are quite popular, and Bohr-Rutherford diagrams are not. Well, that's it for this section.